fans and here in the room. I'm glad to introduce the second speaker of this morning session, with Federico Cacciafesta from the University of Padova. And today he will talk us about dispersive estimates for the Dirac-Coulomb equation. So please, Federico.
Thank you. So first of all, of course, I would like to thank the organizers for putting together this very interesting meeting in such a difficult period of time. And on my side, it's just great having the chance of being here and seeing back so many colleagues and friends I've not seen for a while. And I really hope this will be the chance of starting a new series of meetings. So what I will talk today about is some results we have on the Dirac-Coulomb equation. They are the talk is based on works in collaboration with Eric Serret, which is in Dauphine, and Junyang Zhang, which is in Beijing Institute of Technology. So part of the results are published already, part is not yet, but we plan to finish, well, to have them available in a very, very short time. Okay, maybe I just. Okay, excellent. So I assume that maybe not all of you are extremely familiar with the Dirac equation, so I will spend a bunch of minutes just to give you well, of course, the definitions and the main features of this object, which actually is a very relevant equation in relativistic quantum mechanics. And on the other hand, the understanding from the point of view of dispersive PDE, I feel is quite smaller, mostly if you compare it with the well, more celebrated non-relativistic counterpart, which is the Schrödinger equation or wave equation or KdV or Klein-Gordon. And as a matter of fact, there's many questions that are quite at a fairly simple level that we do not know the answer to. And this system here is a nice example of that. So if I have to compress my talk in a pill, I will just say that what we try to do with the Dirac-Coulomb equation, we're looking for dispersive estimates for this guy, so mainly Strikas estimates. And we are just trying to borrow ideas from papers that are published on the Schrödinger with critical potential, say Schrödinger with inverse square or wave with inverse square potentials. And we try the techniques to fit within this system. And as you will see, even quite easy arguments immediately become complicated. And it's not easy to get corresponding results, like proving Strikas estimates for the Dirac-Coulomb equation is not done yet. And also, I would like to stress the fact that I think, and please let me know if I'm wrong, but what you will see on the board today is pretty much everything we know for the dynamics of this model, right? So if you're aware of other results, of course, let me know, because I'll be very happy to learn. Okay. That being said, let me introduce you what the enemy is. So we are dealing with the system. So the Cauchy problem for the Dirac equation is this guy here. I'm not sure you can see colors. Can you actually see colors? This should be red, because I'm not sure. Well, okay. Anyway,
you can distinguish some
slightly. Okay, okay. It's not crucial though. But anyway, so the unknown function u goes from R4 into C4. That means that we are in 3 space dimensions, and the target space is C4. So this actually is a system of differential equations. There is, of course, a physical meaning why you should have C4 here, because you're just describing a spin of the particle. I'm not getting into any physical details, mostly because I don't know that. So you have one derivative in time, the Dirac equation, the Dirac operator, which is this guy here. Okay, you can think of it, of course, this is a first order differential operator in space, and it is somehow a distorted gradient, as you can see, right? So you write it in terms of the Dirac matrices that are these 4x4 matrices that are written in terms of Pauli matrices themselves that are all here. Right, so what else do we have? We have a mass term here, m beta u, that takes into account the mass of the particle. And let me stress the fact, so this is red indeed, because we, in this talk, we will have to take mass 0. This is going to be crucial for us. This is, of course, a limitation of the argument, but I should mention the fact that this equation is relevant also in the massless case, because in 3D, it should model, as far as I know, the neutrinos, and in 2D, it is used as a model for graphene, which is a very fancy object nowadays. And some of our results, of course, hold in 2D as well. So it's not, it is restrictive, but it's not tragic to take m equals 0. And of course, we are thinking to the massive case too yet. And then we have the Coulomb potential. Of course, it's just constant over modulus of x times nu. This is intended, of course, in a matrix sense, if you want to have the identity matrix here. And okay, so this is a very natural object. I will say something about that later on. And I should mention the fact that this operator here, the Dirac-Coulomb operator, is a difficult object. And even understanding for which charges this guy is self-adjoint is something that has been done just recently. The sharp interval of nu is something that has been done really recently. As far as I know, you can go up to nu equal 1, but this is just known in the very last bunch of years, right?
It's not from the 70s. Come on.
Up to 1, nu equal 1.
Of course.
Really?
Sure.
I thought so. I see refinements of the results by.
That to describe the domain of the closure, but the two threshold, 1 and √3/2
Square root of
70s.
Okay, excellent. That just comes me. Okay, excellent. Okay, so anyway, so the fact that the square root of 3/2 is the first threshold for the essentially self-adjointness, and then you can go up to nu equal 1, even nu equal 1,
Sure.
not smaller than 1. Okay, excellent. Excellent. Okay. Okay, so just no, this is one slide too much. Maybe I should do that. Okay, just some very, very stupid comments on that. I should say that the Dirac equation is, well, when you say very sensitive to dimensions, it means that, of course, you can define the Dirac equation in any space dimension if you want, but it's not as straightforward as defined in the Laplacian, because, of course, with the Laplacian, you just add a second order derivative. Here, you have to be more careful with the construction of the matrices and so on. You can do that. Now, the big difficulty with this operator is that the spectrum of the massless Dirac operator is the whole real line in a massless case, and it is anyway unbounded from below in a massive case. So this is the major difficulty with this model, because well, from any point of view you can think about, from a physical point of view, you have to give meaning to negative space energies. From a variational point of view, you have an energy which is not bounded below. And from a dispersive point of view, you don't have a positive energy that bounds HS norms. So the classical argument, like using the energy to bounce HS norms, does not work in this case. So, for instance, as far as I know, there is not pretty much nothing except for very peculiar results is known for well-posedness for nonlinear Dirac equation with large data. Okay, if you want global well-posedness, you need small data, except for some very peculiar structure you can get. Right, now the good news on the other hand is that, of course, yes, right, sorry. Yes, okay, sorry, I was scared. I uploaded the wrong talk, but it's not, it's the right one. Okay, the good news is that the Dirac equation is deeply connected to the wave equation, because if you square the Dirac equation, you obtain a system of decoupled wave equation, right? So this is because, of course, the Dirac operator is a square root of Laplacian in some sense. So everything you know for the free wave equation holds for the free Dirac equation as well. Especially here, in the following, we will be interested in the Stricas estimates for the Dirac equation. Here, I just recall what the Stricas estimates are. Okay, this is just the same ones for the wave equation. Of course, when you have potentials or nonlinear terms, especially in low regularity setting, you have to be much more careful, because this squaring trick will just destroy any structure. So it does not really work properly if you want to squeeze any detail of the structure of the operator. All right. Okay, so this is what I just said before. This the same estimate as before. It should not be here. Now our question is, yes.
The H norm is based on L2 or L2?
That's based on LQ, of course. Yes. Is it wrong twice? Yes, it is actually wrong twice. That should be LQ. That, of course, is modulus of d to the power there in LQ. Sure. Sorry about that. Yes, that's a misprint. Now, natural questions. Do these precast estimates hold in presence of external potentials? This is something that has been investigated starting, I guess, from the 90s, but maybe even before. And the situation is quite clear, and it is here. So for Schrödinger, we know pretty much everything. So for Schrödinger, you know that if the potential is small, and when I say small, I mean it decays faster than the critical level, and the critical level is given by the scaling. So it is going to be the homogeneity degree of the operator. So for potentials that decay faster than in the Schrödinger case, 1 over modulus of x squared, you typically can prove Streakers estimates, and then you can do that through the standard Kato smoothing estimate argument. On the other hand, for potentials that decay slower, you are able sometimes to prove some counterexamples to dispersion. And then, of course, you have the critical level, which is the difficult one, which for the Schrödinger equation is 1 over modulus of x squared. For the Dirac equation is 1 over modulus of x. So now you see that when I say critical, it means that it's critical with respect to the scaling. And that means that if you scale the equation with the scaling critical potential, it just stays the same. Here it's crucial to have no mass, because if you have a mass, that won't scale, right? So here I'm forced to have, to begin with the massless case. I should say also this, the Dirac-Coulomb model apparently comes out in quite a number of natural settings. I will mention just 2. If you look for instance, to model the dynamics of a nuclear dynamics, then you have equation for electrons and the equation of the nuclei, and you typically want to couple them for a Coulomb potential. That seems the natural, somehow might seem the one first natural thing to do. And there's another thing. If you look, for instance, for the dynamics of the direct equation on curved space with some spherical symmetry, then you will see critical potentials pop up in that situation too. So it seems to be quite a natural question to investigate the Dirac-Coulomb dynamics, besides, of course, the purely PDE dispersive point of view, which is, a dispersive PDE with a critical potential. Yes, and so this is our aim right here, right now, and proving estimates for this Dirac-Coulomb equation. So our inspirations really came from a paper by Burg, Planchon, Stolker, and Tavil-Darjadeh, which is now 20 years old almost, and it is on the Schrödinger n-wave equation with inverse square potential. And so I will spend 3 slides just to tell you what the basic idea of this is, and just to try to convince you how just this quite relatively simple argument becomes quite delicate and full of technicalities if you just try to transpose it to the Dirac-Coulomb model, right? So what is the idea? Of course, you have this Cauchy problem here, initial data f of x. Now, here I'm just being general, so this can be done in any space dimension, but you can think n equals 3, and you have the critical, the Laplacian plus inverse square. What's the tools? So what's the only tools you need? You need spherical harmonics decompositions, of course. You need Hankel transform. The Hankel transform is going to be crucial. And then all the technicalities driven by the Hankel transform will be crucial. What does that mean? The Hankel transform somehow is just a projection on 2 Bessel functions. That's what it is. And so you will need to deal with integrals of Bessel functions. Luckily enough, there's many things that are well known on integrals and Bessel functions, right? So just to tell you now let me try to convince you very quickly what the idea is and where the difficulties are. So maybe here you just can think about the case alpha equal 1 over 4, because this is what you really look for. So you have no derivatives here, and you have modulus of x to the -1 here. And to those of you that are familiar with the Kato smoothing arguments, if you just, well, you should understand quite clearly that if you have the estimate at the modulus of x to the -1 level with an inverse square potential, you get Strika's estimates almost for free, almost for free. You just have to play the Duhamel argument twice. So this is the level you want to look for. It's 1/4, right? Right, so you look for this estimate here. You take f. Okay, the result is quite nice, meaning that if you require orthogonality to some of the spherical harmonics, you get a better result. But just take any initial data f in L2, that will be enough. So how does it work? Yes, so you use spherical harmonics decomposition, and you look like at the radial equation. This radial equation is just solved by somehow Bessel functions. So you want to use the Henkel transform. If you use the Henkel transform, what does it mean? Now you can really forget about the angular part because it will play no role in this argument, because you're working at the L2 level. You have these very nice properties that are, I would say, well known, but maybe, well, decently well known. But most of all, they will allow you to define fractional powers of the operator A mu, right? Because you apply H mu here, which is just an isometry, and it's the identity if you square it, and then you get this representation. Now, of course, you have to write down explicitly what the integral kernel here. Keep in mind, this is the bad part, right? So to write down this guy, you will have to integrate products of Bessel functions somehow with some weights. Once you have that, the whole proof of the local smoothing is right here. You write the L2 norm. You use Henkel transform. So what the Henkel transform really does to your system here is just what the Fourier transform does to the free equation, because it just translates the equation in a multiplication operator. This omega square, I should have stressed that is omega square is just a multiplication times modulus of x squared, right? So you apply Henkel, you get a very easy equation somehow. You apply Fourier transform in time. You do write few things. And all you need to do, you see, these are really equalities that they are not even inequalities. This is really equalities behind some, besides some constants that are hidden here. But you have equalities, and all you need to do is proving that this kernel here just has the right weight, I mean the right behavior in tau, and the constant C mu is bounded in mu, because you will sum, of course, in mu, and you need this not to blow up. This is the whole thing. Okay, right, so maybe this was, of course, a little bit too fast, but just what happens if you try to take this strategy, which you have to agree, it's quite straightforward, and you just try to move it to the Dirac equation. So just to repeat what is important: spherical harmonics decomposition, Henkel transform, which is the projection onto Bessel functions, and integrals of interacting Bessel functions, proper control of that. These are the three tools. What happens if you do this with the Dirac-Coulomb case? Now you look for the same estimate as the other case, and of course the best thing ever would be to get A equal 1/2 here. If you get A equal 1/2 and B 0, then again by the standard trick of local smoothing, you would get Strika's estimates for the system. There is no mass. We have no mass. That's crucial. That's crucial, of course. Otherwise, you would have to project away from the eigenvalues. That's crucial, of course. That's another point why having no mass is absolutely crucial. Right.
In this case, self-adjointness of the operator is.
Yes. Here it is.
You work in the domain of self-adjointness.
Yes.
Not the
Yes.
extension of.
Yeah. Here actually, we will have even farther. There's many. Yeah.
Or it's not self. Essentially,
It's one realization.
Yes.
Now it's the result is transparent because everything goes into the constant.
So it is not essentially self-adjoint.
Actually,
There is parameter.
There is a parameter.
But if you want to, we can even think, we don't care actually too much about that. So we will have further restriction on these, by the way. So we can even think to be in the domain of essential self-adjointness, right? This is not really the point of our argument, right? So what are the big problems here? Well, first, very stupid. When you have systems instead of scalar equations, you have to be more careful. But this is very trivial. The first seriously bad news that the spherical harmonics decomposition does not really work for free. That means that if you take a radial function and you take the Dirac derivative of a radial function, that is not going to be radial anymore. So you cannot work onto one-dimensional spherical harmonics decomposition as for the Laplacian. What you have to do is just to, of course, look in literature, and you will see that there is a counterexample, not a counterexample, a counterpart of the radial decomposition for the Dirac equation, which is called partial wave decomposition. And it is pretty much the same, but it works with, it decomposes the space in two dimensions. That means that you will not work onto one radial component, but onto a couple of components. And the Dirac operator in radial coordinates is going to be a matrix, a 2 times 2 matrix. Okay, that is not so bad, but it is worse, of course, than being with just one scalar equation. And now the best part, well, the worst part, I would say, is that I'm gaining some suspense here. The building of the Henkel transform is not really for free. So if in a way what happened for the Schrödinger equation, you just looked at your restricted equation and you already had cooked up the Henkel transform because it's the projection onto Bessel functions. Here you have to build one. And how you build one, of course, what you want to do is just to project into the spectrum of this guy. And the spectrum of this guy, when I say spectrum, I mean, of course, it's absolutely continuous. So it's a approximated eigenstate. This spectrum looks really, really, really bad. And you will see this is going to be the worst part of the whole thing. That means that having to do with eigenfunctions, generalized eigenfunctions of the Dirac-Coulomb operator is very annoying because it involves special functions like confluent hypergeometric functions, Whittaker functions if you want, or Kummer functions, you can call them many ways around. And you will have to prove estimates on integrals of interacting eigenfunctions, and that is very annoying. Okay, so this is the difficulties you have to face if you want to prove this estimate here. This is the theorem we had in collaboration with Eric, and if you see, it just very, very much looks like the result by Björk-Planchon, Stolker, and Tavil-Darjadeh. That means that we have a local smoothing estimate in with a certain range of weights, which if you want, you can make wider, provided, oh, I did not define this yet, but it will be in the next slide. But this just means that if you take an initial data that is orthonormal to some of the first spherical harmonics, you get a wider range of exponents here, right? But notice that you will never, ever, ever get alpha equal 1/2. And that is the worst news here, because I know that everybody thinks that this estimate in the case alpha equal 1/2 fails, but I've never seen an explicit counterexample for that, and I would be very happy to see one so that I will be able to abandon completely this. If you had the estimate of the alpha 1/2 level, then you just for free would get all the family of Stricus estimates, as in the free case, right? And notice that we cannot improve that, not without, I mean, you can pay derivatives here, you can do pretty much everything you want, but you will not get alpha equal 1/2, right? Okay, so this is smaller. I know, I hope you can read it, but as a disclaimer, I can tell you that when it's smaller, it's boring and it's less relevant. So don't worry too much about that. Here, I'm just giving you, of course, if you are very interested or you want to start working on this kind of things, I will give you references. But this is how it works, the partial wave decomposition for the Dirac operator. You see how bad it looks. So you see you have these two-dimensional decompositions. Here, omega plus and omega minus will be vectors of spherical harmonics. You have these parameters that will vary in some range, but what really is important for us is that this decomposition works properly as a decomposition between Hilbert spaces, and you have radial coordinates here. And with respect to this decomposition, the action of the Dirac-Coulomb operator is just this radial matrix here. Okay, so this is the analog, if you want, of the A nu operator that I've written for the Schrödinger with the inverse square. It doesn't look so bad, but it is a system. So Kj here is an integer, by the way. Okay, Kj is integer. You can just neglect, we will work at the L2 level for the angular part. This is the first thing we do. So you can just forget everything that comes from the angular decomposition. That does not play a role. So this is, just keep in mind if you want this guy here. Yes, and this is the very good part, at least to read. So there is no way around it. You have to work with the generalized eigenstates of the Dirac-Coulomb operator, which are well known. I think I learned them in the book from Landau-Lifshitz in the 70s, maybe, but maybe it's known like forever. And you see how bad it looks. So you have gamma functions, you have powers, you have oscillations, and you have, most of all, you have, and this is small on purpose, you have confluent hypergeometric functions. And there is, so these are a series of functions, it's written in series with Pochhammer symbols. I don't want to get into technicalities, but just try to somehow discourage you to. What?
So I understand you don't have a personal relationship with special functions, and that's perfectly understandable. But you know, they have very clear asymptotics, they're exponential.
Yes.
All what you need is estimates of that sort, and they're very, So why are you downplaying them so much? They're innocent.
Well, yeah, they're
don't like them. I think very much.
Okay. Okay, anyway, so yes, mostly because I lost many months trying to integrate them somehow, and
you don't have to. You want to estimate.
Yeah, trying to estimate them. Just estimating them was quite painful. But okay, I will tell. I hope I will tell you. So then now that you know that eigenfunctions exist, you just can define just the Hankel transform. Here there is some algebra you have to deal with because you want to project onto positive and negative part of the spectrum. So you have a matrix, you have this that works perfectly. But you see, here the thing is that if you just project into the spectrum in frequencies, the operator will become a multiplication operator, right? Okay, so you have pk, you have the inverse of pk that will be just some kind of inverse adjoint of the matrix. And if you want to define the fractional powers of the operator, you will have to deal with this kind of guys, right? So you just have uk, and you have the product of these matrices. That will be just products of eigenvalues, eigenfunctions of the Dirac-Coulomb operator. So now here, what you get is just the copy-paste the strategy from Buch-Penchant-Stoker and David-Darjabet somehow. You use the partial wave subspace decomposition instead of the spherical harmonics decomposition, of course. You use your modified Hankel transform, or we can call it somehow relativistic Hankel transform. And then you just follow the slide I showed you before. And everything you need to do is proving estimates on the integral of this guy here. Then you just do a triangle inequality, and then you're done because you're true in the angular part, and then you're okay. So what you really have to estimate is this guy here. And this, of course, I'm quite negative with these functions because it took us quite some time to prove this estimate, because you want this guy to be bounded in gamma. This behavior here is not so hard, at least in my memory, because now it's 8 years that we've done it. But the problem is the boundedness in gamma, because if it's not bounded in gamma, you get not the sum. You cannot sum for general data. Of course, you get getting the result for radial data is not so hard, because you can take any gamma here and or a finite number of gamma, it's fine. But if you want convergence, then you need boundedness on gamma, which means k, which means the quantic number, right? And this is not so trivial, because these functions are, well, okay, they're just series. You know some stuff, you have some integral representations, you know some asymptotic, and then of course, but one thing is that, one thing is an estimate on a series on this constant here, and it's quite on the threshold in my memory. So it is not that you have much room to expand yourself. But this is the first thing first. Now, just a few comments how. I should say this. So the strategy now, we realize a posteriori, but maybe this was quite well known already. It's flexible, meaning the Hankel transform method is very flexible. It works in 2D. So the result we have works in 2D as well. And it works, for instance, if you want to do the Dirac equation with Aharonov-Bohm magnetic field. I should mention that if you want to work in the Aharonov-Bohm magnetic field, for those of you that are familiar with, it's a two-dimensional model, by the way, things are much easier because the eigenfunctions are just Bessel functions. So essentially, there is not so much you have to do besides the work from Björk-Planchon, Stalker, and Tavil-Dajardin, because most of the computations will work here as well. You just have to be a little bit careful with the self-adjoint extension. You have to be careful with the index of the Bessel functions, but things work. On the other hand, as I told you, the estimate fails. At least we think so. We're nowhere even near to understand it. I mean, it does not work in the case at the level modulus of x to the -1/2. That would be the one that allows to recover Strika's estimates, right? So it does not. This estimate, as it is, of course, it is interesting in its own, but it does not help like for nonlinear, well-posedness models, because you want to have a stable Strika's estimates to be happy to study global solutions for nonlinear models. And so we wonder if there is any way to prove Strika's estimates without going through local smoothing argument, right? So you have to forget somehow this, if you want, perturbative setting, and you want to try and see if there's a way to englobe the eigenfunctions into the propagator and prove the estimates directly on the Dirac-Coulomb equation. So this is what has been done. This is the other part, which is not really done yet, but I'm positive enough that I can talk to you about this. So can we prove Strika's estimates without using local smoothing, right? So what can we do if you have a Dirac equation, well, a dispersive equation with a potential, and you cannot use Kato smoothing argument? Well, what you do is just you try to write down somehow the propagator with the whole, with the Coulomb potential plugged in already, and you try to estimate Strika's starting from the very beginning. Of course, you will have to face again the eigenfunctions, and I will tell you what is needed in this case. So this is the idea. I learned this from this paper here by Miao, Zhang, and Zheng, which again was on Strika's with inverse square, and it is quite relatively easy, I would say. So it against the starting point is just always the same. So it's partial wave decomposition and Hankel transform. So this just works the same for our case and for the Schrödinger with the inverse square. You just go back and forth if you want. Then what you want to do is just to prove Strika's for the fixed k. That means a fixed angular level, and with localized frequencies, right? So you localize the support of the function into an annulus, and then you just do some scaling argument and the dyadic decomposition. So this part here is okay. This part here is quite standard too. The problem is hidden here, because once you have the Strika's estimates for localized frequencies, I would say as long as I understand it, it should be okay. So here is where the efforts have to be focused. You start from this representation, which again is driven by our Hankel transform. So you just project the initial data. So Fk here is just the coordinates, the radial coordinate of the initial data. Just keep in mind that, again, the angular part will just be negligible because we'll be L2 in the angular part in any case. So this is going to be fine. So I'm projecting onto the initial data, then I propagate, and then I project back to have the propagator of the initial data. Right, so the crucial point is going to be here, as long as I understand. So what you need is an estimate in this form. So you need, you see, you fix a K, you fix the support of the data in some endless, and you want an estimate. So this is just a posteriori, so it's not really, I'm giving you the result, the estimate that we obtained. It's not really the one you need, but this is what you got and what you expect, also borrowing the ideas from the Schrödinger with the inverse square. But I will get you to the point in a minute. This is the estimate you see for L2 in time. So we take L2 in time because we're just working, if you want, at the endpoint level. Of course, Q will not be able to be infinity, but then we get the interpolation with all the other things. And if you have an estimate of this kind, then you'll be okay. This estimate here will require an estimate. Now here I'm cheating a little bit because alpha, I'm not telling you who alpha is, because again, this is a posteriori. I will tell you what the estimate you want to prove is in the next slide. But if you can prove an estimate of this form, and then you interpolate with some proper alpha here, you'll be happy. So what is that you really need, and what is that you really expect? What you really need is something like this. So the truth is that you have no problems in the origin, because the behavior of the eigenfunctions in the origin is quite fine, especially for a large quantic number. They're not singular, right? They are bounded. The problem will be for large R. Remember that we need bounds on the constant K as well. And for a posteriori, we realize also for R close to K. Why do I say that? Because what is well known for Bessel functions is this estimate here. I don't know if it's well known again, but it's classical. I think it's proved by Cordova and Barceló and Cordova maybe 25 years ago. For large order, you have this estimate here. So you see, for what you have for Bessel functions, you have easy behavior in the origin. You have this behavior here around the, I don't know how do we want to call it, the turning point somehow when R gets close to lambda, and then you have R to the -1/2 for very, very large R. This is what is reasonable to expect, because if you send to the limit to the charge going to 0, your eigenfunctions, of course, will recover the eigenfunctions of the free Dirac operator, which are the Bessel functions. Just keep in mind we have a slightly different normalization here, so you have this additional term. So this is exactly what one would hope to be able to prove, right? And I should say this. So, of course, what we tried immediately to see is that, can I just steal the proof done for Bessel functions? And we went down and see how it works. It is a little bit cryptical because it's very short, and it's just based on oscillatory arguments and on what is called, I think, the Schlafly's representation of Bessel functions, which is a very precise representation of Bessel functions that we don't have. So we don't have that representation for the confluent geometric functions, that is for the generalized eigenstates. So there is no way we can just copy the proof for the Bessel, and we have to do the proof ourselves.
Also, that limit is treacherous because in general, generalized eigenfunctions don't converge to generalized eigenfunctions.
Oh, sure. So
it's inspiring, but quite treacherous.
Sure. You just cannot get it by continuity, say, or anything. Of course, it's just you just see what you expect to have, what you hope to have. Maybe so it's even more fair. I completely agree. What you hope to have is something that, I mean, you wouldn't be surprised to prove this. That's what I mean. Yeah, and so our starting point had to be another integral representation, which is this representation here. And you have to prove estimates on this guy here. And this is, again, just took us quite some work. And I say quite some work because we failed through integration by parts. So integration by parts, as long as we can see, is not going to work. So you see, it's tempting, of course, because how many integration by parts you can do? Essentially gamma here, right? So anytime you do an integration by parts, you gain a rho. So the behavior in rho is going to be fine. It's going to be rho -1. But then you have what is surprisingly bad, and we could not deal it with, is that when you have say half derivatives here and half here, you have many terms. So the number of gamma, the growth in gamma seems not to be under control somehow. So maybe it's just because we got the computations wrong, maybe we did something wrong, but it seems that we could not deal with that just by purely integration by parts arguments. So what did we do? We did them first of all because we were desperate. We just proved it for a fixed level of eigenfunctions, right? So if you fix k, that's going to be, I would say, easy. You don't have to worry for the behavior in gamma. And then I'm not going to I will skip this because it's not. It is what you expect, right? So you have boundedness in the origin, which is fine, and you have rho -1 for very, very large R. You don't have to worry about gamma again because you're fixing k. And this just integral representation into integration by parts. And as a consequence, just playing that game I told you, you get a nice Ficus estimate with radial data, which is, I mean, it's fair. I mean, you have Dirac-Coulomb, and you have for nu you have this restriction that is a byproduct of our proof. So it's not even getting to 1, but it's larger than square root of 3/2. So it's just in between if you want. And you have for initial data, which have enough regularity and live in an angular space. We're taking k equal 1, but we could take any other one, of course. You get Ficus estimates on the endpoint board. This is, well, fair, not revolutionary, of course, because we would love to get the estimates on the full spectrum. And in fact, and I'm really crossing my fingers here because we're checking and checking. It's quite a long proof. We managed to prove with Eric and Junyoung the same estimates you expect for Bessel functions. Just the only difference you see is the normalization one. So you see this, instead of having rho -1/2, you have rho -1. And here, instead of using oscillatory integral like integration by parts, you use a method that's called steepest descent method, which I'm probably not going to talk about because maybe you're all familiar with that, but it's just a tool that allows you to deform the integral of a function. You use complex integrations and you follow what's the steepest lines, and then you can use the Laplace method to approximate the values of these eigenfunctions, of these integrals, essentially on the maxima of the functions you are integrating. So this is a quite well-known tool is an asymptotic analysis estimates, but it's quite delicate to deal with to make it work on our integral representation. So I'm just saying it. Well, I'm quite confident about that because we checked it several times, but just will take us a few days more. And if you prove that, then this result, which looks very much like the other one, but now I can prove any initial data. U0 in HS, and then you get Ficus estimates with well, we can call it loss of angular derivatives if you want, or angular regularity space of as you prefer. And the initial data will be in H.S, and you still have the same as a byproduct of the proof. You will have still the same bound on Q here. All right, and I think that's all I wanted to say. So maybe I'm a little bit short, but thank you very much for your attention.
Thank you, Federico, for the very nice talk. So it's time for questions. Let's start with some online questions. So please, if you have any question, just unmute yourself and ask. In the meanwhile, if someone in the room has some question. Vladimir?
Small question about eventual applications to some nonlinear problems, because there are interesting interactions that can be described with nonlinear models, where Strickert estimates unfortunately are not, I would say, cannot solve the problem, even they are not. What kind of applications do you plan to do?
So, for instance, I mentioned two at the beginning, but I'm glad to say them again more clearly. We saw this kind of things appearing in two different situations. One of them is when you do the Dirac. I'm not sure I can call it an application, but somehow when you see them, when you study the Dirac equation on spherically symmetric manifolds. Right. So the dynamics of the Dirac equation on spherically symmetric manifolds, if you use this partial wave decomposition, of course, you have to define the operator and see how it's written. But if you write down the operator in a spherical harmonics decomposition, you will see pop up a Coulomb potential. That means that if you are able to prove Strickerts for Dirac-Coulomb, you are able to prove Strickerts on spherically symmetric manifolds, weighted Strickers and spherically symmetric manifolds, which is quite nice because, you know, geometric PDEs are quite nice. So, and that's the first thing. Another maybe more relevant, well, some mathematical physics model we're studying here. I'm not completely sure it's a very how do you say justified, but we borrowed this model from the non-relativistic case. So you take a Schrödinger equation for the electrons, and you couple the dynamics with dynamics for the heavy nuclei, which is going to be a classical dynamics, and the interaction between the electrons and the nuclei is going to be via Coulomb potential. In the Schrödinger case, everything is well known, and you use Strickerts to prove global existence. Here, then you will also have a nonlinear interaction because the electrons will interact themselves, like with a non-local potential, right? For the Dirac case, you don't have the Strickerts. If you had the Strickerts for Dirac with Coulomb potential, of course you have to be more careful because there will be moving potential, but so on. Starting from the static one, that'll give you some kind of well-posedness for some relativistic nuclear dynamics. I'm saying it with all the respect that these kind of things deserve, but for a toy model of that, you could prove global well-posedness for that kind of thing. So you see, Coulomb potential somehow appears quite naturally often. I should also say this very last thing. In the paper by Buch, Planchon, Stalker, and David Lajarret, they explicitly mention in the introduction that the model they study might not be so relevant, the Schrödinger with inverse square, but they hope their strategy will hold in some more relevant cases like the Dirac-Coulomb. So they mention them themselves. So we tried to do that. We did not cover the whole thing, but we tried our best, and we're not down yet.
Yeah. Other question online? Someone? If not,
why don't you go through resolvents? And then
It's just to say
resolvent and then inverse Laplace transform.
yes, that's
Yeah.
yes, that's a very, I mean, of course with
Because the resolvents are explicit.
yes, but they quite look like
Special functions, special like.
no, but this is this two. I mean, you can write the green function, that's explicit, and then you do the inverse Laplace transform. That's pretty much what you say.
Also a big rotation.
You have to do some, be careful a little bit. Yeah, I mean, in principle, it works, but we cannot do the computations. That's the thing. I completely agree with you. The idea will work.
okay, Nico, please.
I understand that the range of mu is the very important, but it can be, you can say something in terms of non-self-adjoint potential. So you can do is complex.
So the question is, I just repeat the question for the onlines. If we can say anything about new complex, no, yeah, or well, no, or also new larger than one, I guess it's going to be the same, if you want. The answer is quite frankly, no. Also, if you see, we have this bound here. Of course, we just assume that If it's not self-adjoint, I have actually no idea, because we use when you do the reduction onto a spherical harmonic space, you use Stone theorem to say that the reduction is you can reduce the propagator at the radial level. So if you have non-self-adjoint operators, I have no idea whatsoever. No, even in the self-adjoint case, I have pretty much no idea. So
For very, very small modulus of new complex, you shall have a nice definition of the operator, and eventually obtain the estimates are perturbation, epsilon perturbation of the estimates with 0.
Yes, probably if you take nu plus epsilon, I epsilon, yes, probably yes, I would say so. But
for applications, this is missing. Application. So when you attack some nonlinear models, then this small mu is not good.
Other question in the room? Lucrezia, please.
And you mentioned that for the magnetic Dirac matrix Dirac, you would prove something for the 2D case and the Arnold case, but more in general, you say.
you mean with scaling critical magnetic two-dimensional potentials?
Yes, why not?
So yeah, apparently I can play my game as soon as you give me an operator you know the generalized spectrum of, and it is scaling invariant, because you want, if it's not scaling invariant, you're not you're gonna miss this property here essentially. Because if you see, for instance, if you have a mass, okay, this is the Schrödinger. I should go to the Dirac. Where is it? If you have a mass here, you would get omega square root of omega minus mu somehow. So this is not going to work properly. You would get to some kind of Klein-Gordon propagator, and going back and forth is not going to be the same. But on the other hand, yeah, if you have a scaling critical potential, magnetic potential, if you want, and you know the spectrum of that will work. For instance, with Luca, we also did the wave equation with the fractional Schrödinger equation with critical potentials. We knew the spectrum of. So it is flexible. The strategy is just very, very flexible. But unfortunately, on Dirac, you just have to stop at the local smoothing level. Thank you.
Online, no question? No. Federico, sorry, can you explain again what is the point in the proof that prevents you to obtain the exact cut smoothing to go to the endpoint case?
Oh, it is, yeah, I did not say that at all, but it's when you, it's hidden here.
Okay.
Where is it? It's in this integral here. When you write down this integral, you will get a constant that is gamma of 1 minus 2 alpha. Okay. Right, so you get a gamma in 0 regardless of the quantic number, regardless of the regularity, regardless of everything. So there is no way that you can get alpha equal 1/2. Mm-hmm. And that's because, I mean, you have to plug the series of this guy here in here. You do the products. You have to take real and imaginary parts, and you see that alpha equal 1/2. It's just, I mean, it's just purely technical, but it's just that. You need them just not to have a gamma function in 0. And we've found no way around that.
But I think that maybe it's the kind of, maybe it can be that really is not true, or no, maybe there's no way to, you mentioned maybe it's.
I think it's not true. I think that it should not be true in the free case for the wave equation. Even that, I don't know of counterexamples explicit. Please let me know if I'm ignorant on that. But I know that it's highly recognized to fail for the free wave and free Dirac. So there is really no way to expect that it holds for the massless Dirac.
Okay. So if there are no other questions, we can thank Federico again.
Thank you.